Right. So what are we at? We're at tutorial 11, the final tutorial for the semester. So in today's tutorial, we are extending our work on failure theory by looking at the maximum distortion energy failure theory. And as you'll see, this is really just a small incremental piece that's added onto the work from combined loading and stress transformation. So just like as was the case with the maximum absolute shear stress theory, most of the work in these problems is all the stuff that leads up to the actual application of the failure theory. So it's all the combined loading and the stress transformation. But hopefully, by the end of this tutorial, you'll have a really good grasp on that. So let's go ahead and look at the problems. I've got two problems picked out here for you. So we'll work through both of those. The first problem is sort of a four-part multi-step problem. And none of the parts individually are long or complicated. But hopefully it gives you a good feel for where we are now in the course and where we've come from, right? Okay, so I'll throw it up on the board here. So we've got sort of a two-membered pin support here. So there's a pin here joining those together and another pin here. And that's fixed. And another pin here. And this is inclined at an angle of 30 degrees to the horizontal. And then we've got a force being applied up here. And that force is 7.5 kilonewtons. There we go. And this point down here is labeled as point A, and there are some dimensions given. So the distance between those two pin supports is 1.5 meters. And the distance from the point of load application to that pin joint there is 1.4 meters. And then this length here is 1 meter. Okay. And we're also given a side view of pin A. Okay, so looking at pin A from the side. And this side view is merely showing that pin A is a pin in a double shear configuration. So looking something like this here, where we've got the pin passing through the member that goes from A to, let's say, well, the point of load application up here, and then going through a bracket on each side. So here's the actual pin going all the way through here. Okay, so there's our pin in double shear. Okay, so let me read the problem statement for you. It says both the cable and pin A are to be made using stainless 304 steel. So stainless 304 for the cable. Oh, I didn't actually draw the cable. So this load that's being applied here is actually being applied to a cable. And that would be helpful in terms of the text of the problem making sense, or what I just said makes sense. So here's a cable. I'm sorry for screwing up your notes there. And the load is being applied to that. So this is 7.5 kilonewtons. Okay, so both the cable and pin A are stainless 304. The design must have a safety factor of 1.5. Okay, Great. So first part of the problem asks, using the maximum distortion energy theory, determine the required diameter of the cable to the nearest millimeter. Okay. So using the maximum distortion energy theory, determine the required diameter of the cable. Required diameter of cable to the nearest millimeter is what we're trying to find. Okay, I think we've got everything we need to go ahead and start with this. So for our failure theory, if we want to apply the maximum distortion energy theory, just as we would if we were applying the maximum absolute shear stress theory, it all starts with choosing a location, defining the stress state of a volumetric element at that location, or in a 2D problem like this, we can just jump straight to the in-plane element because we know there are no stresses into and out of the plane of the board in this case. And then drawing Moore's circle, getting the values that you need for Moore's circle and applying the failure theory. Okay. So for the cable, we know that, anywhere that we cut that cable, there's going to be the same internal loading condition present, where we've got our 7.5 kilonewtons being applied, and then that's balanced out some of the forces in the x equals 0 by a normal force that's also equal to 7.5 kilonewtons. Okay, so the normal force will cause normal stress over the entire cross-section. Every point in that cross-section will have the same normal stress resulting from that internal normal force. So it doesn't matter which point in the cable we choose to analyze, all points are going to have the same stress state. So let's just pick one. Let's say that this here is, let's label some other points so we have them all set up here. If that's point A, let's call this point B, this point C, this point D up here. So maybe this will be point E then. So the element located at point E, and again, we'll just do this as a two-dimensional in-plane element since we are just dealing with a two-dimensional problem here. Let's set up some axes for ourselves. So let's say this is X and that's Y. So here's our in-plane element with the X and the Y directions. And this internal normal force, it's a tensile internal normal force since it's pulling away from the section cut. So that's going to create a tensile normal stress on the side of this element that's in the section plane. So the side of the element that's in the section plane is the left-hand one. So of course we've got a normal stress due to our normal force. I'll write that as sigma subscript n there, and an opposing normal stress on the other side. And there are no other stresses on this element. So we have all the stresses captured. So let's go ahead and calculate what that normal stress is. So we've got sigma subscript n is n over a, and that's going to be our 7.5 kilonewtons, 7.5 times 10 to the 3 to change that into newtons, divided by our cross-sectional area of the cable. And of course, the cross-sectional area of the cable is going to be in terms of our unknown diameter here. So we've got pi over 4 and then d squared. So there's our expression for the normal stress. So in order to apply the failure theory, we need to take the stress state for this element and represent it on Moore's circle. Okay, so let's draw Moore's circle for that element. So let's set up our axes here. So we've got shear stress plotted on the vertical axis with positive shear stress downwards, and normal stress on the horizontal axis with tensile stress to the right. So we need two things to plot the circle. We need to know where the center of the circle, C, is, and that's given by what? The average normal stress, comma, 0. Those are the coordinates that point C occurs at, because C is always on the horizontal axis. So we've got 0 there. So in this case, we've got the average normal stress is 1/2 of what? Sigma x plus sigma y, right? Which is simply, in this case, sigma n divided by 2. Okay. And that is a positive number because this is tensile. So when we put sigma n in for sigma x, it stays as positive. So we've got the average normal stress is positive sigma n divided by 2. So we can plot the center of the circle. Let's say that that's right about there, sigma n divided by 2. There's point C. Point A is always given by the stresses on the element's right-hand side. Okay. So we've got right-hand side there, right? So the element's right-hand side, now I'm going to erase this highlighting on this edge because I was highlighting that to indicate that that edge of the element was the edge that was in the section plane. But now we want to be looking at what the right-hand side of the element is. So this is the right-hand side there. So the stresses present on that side are sigma n, which is positive because it's tensile, and there's no shear stress. So we're at sigma n comma 0 for point A. So that takes us out here to sigma n, point A. Now, don't let the fact that you're dealing with a stress that's in terms of a variable prevent you from drawing Moore's circle, right? You can still draw Moore's circle even though your stress is given in terms of a variable, just like we've done. So our radius for the circle stretches from C to A. That's radius r. And then we can draw the circle, and of course it stretches right back through the origin and around like that. Okay. So let's talk about the maximum distortion energy theory here. The maximum distortion energy theory says failure will occur in a material when the yield strength divided by the safety factor squared is equal to the first principal stress squared minus the product of the principal stresses plus the second principal stress squared. So in this case, let's look at our principal stresses. We've got one principal stress over here, right? So that is sigma 1, and of course sigma 1 is equal to sigma n. And here's our second principal stress, sigma 2, which in this case is equal to 0. Okay. So looking at this equation then, what are we going to have? We've got sigma 2 as 0. So this is 0, that's 0. So all we're left with is sigma y divided by the safety factor squared equals sigma 1 squared. Take the square root of both sides of that equation, and we've got failure will occur when the yield strength divided by the safety factor is equal to the first principal stress. So we can complete this now. And what we need to do here is just substitute in the yield strength, and let's look at our material property table for stainless 304 steel to get what that is. So 304 stainless steel, yield strength in megapascals, 207 megapascals. So we want 207 times 10 to the 6 divided by our safety factor, which was 1.5, is equal to sigma 1, right, which is sigma n, which is 7.5 times 10 to the 3, 7.5 kilonewtons pi, divided by 4, our unknown diameter squared. Okay. All right, solve that, and you get, let's see what I got when I did it. I got 8.3 millimeters. Okay, problem said that we want it to the nearest millimeter, right? 8.3 millimeters. We have no choice here. We have to round up to 9 millimeters, even though 8 millimeters is closer, right? If we rounded down to 8 millimeters, then our safety factor would be lower than 1.5, and we can't do that. So this needs to go to 9 millimeters here. Okay. Questions about that first part of this multi-part problem? Okay, hearing nothing. Let's look at the second part of the problem then. So let's do a little bit of erasing here. We can get rid of that. We can get rid of this. We know what our safety factor is and that we're dealing with 304 stainless now. Okay, that should give us enough room for the second part of the problem. Okay, part 2. Part 2 asks, referring to the cable, show that for something under this state of stress, the maximum distortion energy theory is equal to both the absolute maximum shear stress theory and the simple method of failure analysis given by sigma max equals sigma y divided by our safety factor. Okay, show that for cable, max distortion energy theory is equivalent to, we said the maximum absolute shear stress theory, which is tau abs max is equal to the yield strength divided by 2 times the safety factor, and show that it's equivalent to the simple method of failure analysis given by sigma max is equal to sigma y divided by the safety factor. Okay. So if you remember, let's deal with this one first. When we first started the course, like way back in lecture 2 now, and we first introduced safety factors, we were using safety factors by just simply determining fail based on the maximum stress and equating that to the maximum stress in the object and equating that to the yield strength divided by the safety factor. For the cable has a stress state that looks like this, where this is what's called a uniaxial state of normal stress, because we only have normal stress, and the normal stress is only in one direction. There's no stress here in the vertical direction, and there's no stress in the direction into and out of the plane of the board. So we've just got normal stress in one direction. When you have an object that's experiencing normal stress in one direction, a special thing happens here where when you take the maximum distortion energy theory and set your second principal stress equal to 0, which it is because there's no stress in the vertical direction, this distortion energy theory reduces down to this equation here. And look at this compared to that equation. We've got sigma y divided by the safety factor, sigma y divided by the safety factor equals the maximum stress equals sigma 1. And sigma 1 is the maximum stress, right? So these two are perfectly equal for objects that are experiencing uniaxial normal stress, okay? And that's really interesting because it means that what you were doing back in lecture 2 and lecture 3, it's all still okay. You weren't doing anything wrong back then. The problems were designed so that they were all uniaxial stress. So knowing the failure theory now, or knowing about the failure theories, wouldn't actually change what your answer is for those problems. So what this really tells you is that if you come across a problem that's uniaxial normal stress, then you don't need to go through the process of drawing Moore's circle and applying the failure theory. You can just use your normal or your simple form of failure analysis, which is maximum stress equals yield stress divided by safety factor, or if you're dealing with brittle materials, the ultimate strength divided by safety factor. Okay. So what about the absolute maximum shear stress theory? Well, let's explore that. So let's take that one down here. To apply this theory, we've got the right-hand side of this taken care of, but the left-hand side, we need what the absolute maximum shear stress is. So tau abs max, right? When we find tau abs max, what we have to do is look at the signs of the principal stresses. And remember, the rule is that if both the principal stresses have the same sign, so they're both on the positive or both on the negative, then the absolute maximum shear stress is the larger of the principal stresses divided by 2. And if the principal stresses have opposite signs, then the absolute maximum shear stress is the maximum shear stress from the in-plane Morse circle that you've drawn. In this case, there's the question of, like, is 0 positive, like sigma 1, or is it negative? And it actually doesn't matter, because here, if you think about, if you take it as negative, for example, so you take the principal stresses to be opposite signs, then the absolute maximum shear stress would be the maximum shear stress, which is equal to the radius. And if you take them both as positive values, then the absolute maximum shear stress is the first principal stress divided by 2, which is also the radius. So in either case, for this problem, the absolute maximum shear stress equals the radius, and the radius equals what? Sigma n divided by 2. Right? So now, looking at this equation, what we have is sigma n divided by 2 is equal to the yield strength divided by 2 times the safety factor. We get rid of our 2's. And then again, we have exactly an equation that is equal to the simple method of failure analysis and equal to the equation that we get from the maximum distortion energy theory. So for a state of uniaxial normal stress, the maximum absolute shear stress theory is equivalent to the maximum distortion energy theory. Okay. All right. Any questions about that? That's a pretty simple thing to understand, but it's powerful in the fact that if you appreciate that, then you don't have to worry about applying these failure theories to cases of uniaxial stress. You can just jump right to the simple method of failure analysis. Okay, let's move on to part 3 then. And before I do any erasing, let me just see what part 3 is. So it says, using the maximum distortion energy theory, determine the minimum required diameter of pin A. Okay, so let's do some erasing then, and we'll do that part of the problem. So we're moving on from the cable now to the pin. different because, of course, the cable is under state of normal stress, and we know that pins are primarily loaded in shear. Okay. Now, you probably got this by now. There we go. Okay. So if we want to, let me write down part 3 on the board. Okay, using the maximum distortion energy theory, determine the minimum required diameter of pin A. So the required diameter of pin A, use the distortion energy theory. Okay, so that's what we want to do. All right. So again, if we want to apply a failure theory to the pin, the first thing that we want to do is look at what sort of loading that pin is under. So let's figure out the support reaction forces at that pin joint, and then we'll transfer those forces from member AD onto the pin and draw a free body diagram of the pin, and then we'll determine how to section cut it and look at what the internal forces are and think about which point we want to choose for applying our failure theory at. Okay. So to figure out the support reactions at point A, let's change this into a free body diagram here. So let's erase those supports here. Now, if this is pulling forward, then we're going to have an upward load here, By, and a horizontal force here, Bx, and of course, BC being a two-force member, the vector sum of those two support reactions need to point along member BC. And then let's erase this one. Okay. Go. By being up, AY would need to be down, and BX being that way. Well, we don't know about AX, but it would make sense that it would be this way as well. Now, it's not important that you get the directionalities of those right, of course, because the math will tell you if you're wrong and you need to switch the directions. Okay, so in order to figure out the support reactions at point A, what are we going to do? Well, if we take a sum of the moments about point B, then By, Bx, Ax, those all are not present in those equations because they pass through point B and don't create a moment. Ay will create a moment, and the 7.5 kilonewton force would create a moment, so that would give us Ay. So let's do that. So sum of the moments about point B has to be equal to 0. That gives us what? 7.5 multiplied by 2.4 is equal to Ay multiplied by 1.5. Okay, that gives us Ay is equal to, refer back to my worked out numbers here, 3. Ay is 10.4 kilonewtons. Okay. And now what are we going to do to get Ax? Right? Well, if we took apart this pin joint now, and there are a few different ways that you could go about doing this, but I think this might be the most simple way to do this. Actually, let's just get rid of that whole thing. There we go. No need to be doing delicate erasing when we can just clean the whole thing off. Okay, let's put our, we've just taken apart a pin joint, so we need to put forces in here. So let's just put CY like that and CX like that. So now, if we did a sum of the moments about point C, both CX and CY disappear, so does AY, and we're only left with AX in the 7.5. So that would give us what we're looking for. So sum of the moments about C has to be equal to 0, has to be equal to 0 if this is in static equilibrium. And that, oops, that gives us what? 7.5 multiplied by 1.4. Said 1.4 and wrote 1.5. 1.4 is equal to AX multiplied by 1. Now, I'm very casually doing this equation here, and I haven't defined a positive direction about point C. And if you look at what I've just done, I've said that this moment has to be balanced by that moment. But if you look at the moment contributions about point C, the 7.5 is acting to rotate the member clockwise about point C, and AX is also acting to rotate the member clockwise about point C. So this really, AX really needs to be in the other direction, okay? But if you were gonna leave this in that direction, what we should really be doing is doing this formally and saying that maybe counterclockwise moments about point C are going to be positive. So then this would be a negative, and this would also be a negative, and this would be a 0. And if we did it properly like that, then AX would come out as a negative value, telling us that our assumed direction of AX here was wrong. So AX comes out to be negative 10.5 when you do that equation. So what do you do when you get a negative? Just what I said, change that to a positive, go back here, scratch that out, and put it the other way, AX. There we go. All right. Any questions so far about any of that? Of course, that's just the statics part of the problem. Everything looks good in the chat, so we will continue. So let's look at the forces now on the pin. Okay. So what have we got? Maybe if we draw this pin in sort of 3 dimensions here, we'll have a good view of looking at what the forces are like that are acting on it. So let's do it something like this. Okay, so this is pin A right there. Okay. Loads being applied to the center of the pin from member AD, and then bracket applying opposite forces, half on each side. So if AY on the member is downward, then AY on the pin has to be upward. So we've got a force like this. There's AY. Okay. And if AX is acting towards the right here on the member, then it needs to be acting towards the left here on the pin, or that's AX rather. So the vector sum of those is a force vector like that, and we'll just call that FA. Okay. So resisting FA are two forces from the bracket, right? Force from this side and a force on this side. So this is FA divided by 2, and this is FA divided by 2. All right, now if we do a section cut somewhere in the pin, let's say there, let's get our section cut here, so make that a little bit larger like this. Okay, we've got our force FA divided by 2 being applied, and that is balanced by an internal force, right, that is going to be parallel to that cut section. So of course this force here is our internal shear force, and that's our internal shear force V, and that's equal to FA divided by 2. Also though, because these two forces are separated by a distance, there's going to be a small internal moment here that is generated, and this is going to be equal to what? The value of this force, if we take the sum of the moments about the centroid of that cut section, then it's our value FA divided by 2 multiplied by whatever this distance D here is. So we've got FA divided by 2 multiplied by D. Now, pins are structured so that they are primarily in shear. So here we don't have any length dimensions. So it is fair to assume that distance D is very small, sufficiently small that this internal moment is very low and the stress due to bending is going to be small. So the primary stress that we're interested in is the stress due to the internal shear force. So where are the stresses caused by that internal shear force going to be maximum? Let's just draw that cross section in 2 dimensions here. So here's our cut section, and actually if we're just drawing it in 2 dimensions we wouldn't see a jagged edge like that, right? We'll just see a round edge like this, and our internal shear force V is acting upwards like that, and we've got our centroidal axis going through that way. So remember, if we're plotting the magnitude of our internal shear stress versus, let's say, height position within the cross section, distance y, for example, then our distribution of shear stresses looks like this, where we've got 0 shear stress at the edges, because if you take a location here and calculate the value of A prime, the portion of the cross section below that point, or a line going through that point, at 0. And then the distribution of shear stresses will increase, reaching a maximum at the location of the centroid. So tau max there. So any points along this centroidal axis that is perpendicular to the direction of the shear force will experience the maximum shear stress. So when we think about finding the required diameter using the distortion energy theory, and we want to analyze the point that's under maximum stress, we want to choose any one of those points there, okay? So let's just take one of them. Let's choose this as our point, and we used D in the last problem. So let's call this point E there then, and I'll erase these other points so we don't get confused about what we're looking at. There we go. So point E is over here. Okay. So let's define some axes for ourselves, our coordinate system here. So in this 3-dimensional picture, we've got one axis going like this, And we've got sort of a second axis going up like that in the direction of that shear force there. And we've got another axis that is what? We're going out like this. Okay. So let's say that this is not a well-drawn coordinate system there. So let's make it like this instead. There we go. That's better. That's better because the pin, the face of the pin here, right, would be in the y-x plane that we previously defined here. So this should be y and this should be x, and then x into y, our z-axis, would actually be going the other way, like this. There we go. Perfect. Okay. So now we're looking at this face here in the XY plane up here. And let's draw our element of material that's located at point E. Okay. Because our shear is acting about an axis that's rotated relative to the XY plane, let's actually rotate this axis here and there. Now we've got a rotated x prime, y prime axis that is in the direction that makes sense for that point there. So let's draw our three-dimensional volumetric element at point E here. Okay, so here's our volumetric element. Nice, and the face of the element that's in the section plane is this front outlined face like that. And the shear stress at point E, so this element is our point E, and the shear stress on that element is going to be in the direction of the internal shear force, so it's going to be pointing upwards, right? So this is tau due to our internal shear force V, which means that we're going to have a negative or a downward shear stress on the back, shear stress over like this, and a shear stress over like that. Okay, and let's just put on our coordinate system here. So we've got Z, and this was our X prime and our Y prime. Again, these primes just indicating that relative to the original coordinate system that we set up, we've rotated that so that our new coordinate system is parallel to the shear stress that we've identified at point E. Okay. All right, so our two-dimensional in-plane element, we want to draw that in the Y prime Z plane here. So looking at the element from the right-hand side. So we'll draw this in a rotated form like this, just so that everything's nice and square now. And the shear stress that would have been on the front here is now on this side. Shear stress there, and shear stress there. So now, in terms of coordinate systems, we've got Y prime in that direction and Z in that direction. And this shear stress is tau V there. Okay, so that's all of the hard part basically done, because now we know that we've identified the point that we want to analyze, and we know what the stress state on that point is. We said that there's an internal moment, and that internal moment is going to be very small if d is small, so that the normal stress caused by the moment is small. At point E, though, because the moment acts around an axis passing through point E, there's no normal stress at point E from the moment, no bending stress. So this element that we've drawn here has all the proper stresses on it now. That's the complete stress state at point E. So we can go ahead and draw Moore's circle based on this point. So let's go ahead and do that. So let's set up the axes for our circle here. So we've got positive shear stress, positive normal stress. To plot the circle, we need point C, average normal stress on our element, comma 0. The average normal stress here, 1/2 of sigma z plus sigma y prime. That's 0, right? Because there's no normal stress. So the center of the circle is 0, comma 0. So the center is right at the origin. And then point A is given by the stress state on the element's right-hand side, sigma comma tau of the element's right-hand side. Right, there's the right-hand side. And we've just got the shear stress tau V on the right-hand side, but it's acting downwards, which is defined as a negative shear stress. So here we have comma 0, comma minus our value tau V. Okay, so downwards is positive, so upwards we need to go to a value of minus tau V, and that is point A, our reference location on the circumference of the circle. Radius extends from C to A, and then we can draw the circle here. Okay, there we go. All right, let's do some more erasing and give ourselves some room to actually apply the failure theory. Okay, so again, we want to be using the maximum distortion energy theory to size the required diameter of this pin. So that theory is the yield stress divided by the safety factor squared is the first principal stress squared minus the product of the principal stresses, second principal stress squared. So let's look at the principal stresses, right? Principal stresses are always where the circle crosses the horizontal axis. Larger of the absolute values is labeled the first principal stress. They're both exactly the same, so it doesn't matter which you label as sigma 1. There's sigma 1 and sigma 2. Both of these are equal to what? Both of these are equal to R, which is equal to our value of tau V. Now the fact that this is a negative is kind of hiding under there, so there we go, minus tau V. So sigma 1 equals R equals tau V, and then sigma 2 also equals R here. So let's put those in. So on this side of the equation, we've got what? Sigma 1 is going to be our value of tau V. So we've got tau V squared minus sigma 1, tau subscript V again. Sigma 2 also equal to tau V, but that's a negative, and we need to pay attention to signs when we complete this equation. So we've got minus tau V there, plus sigma 2 minus tau V. Of course, it doesn't matter that it's negative because it's squared. So let's see what we've got. We've got tau V squared, negative, negative, positive, plus tau V squared, plus tau V squared, right? That's 3 tau V squared. Okay. We can take the square root of both sides of this equation. Sigma y divided by our safety factor is root 3 multiplied by tau v. Okay, so now we're in a good position where we can actually solve this. So let's write down our expression for what tau v is going to be, and then we'll come back and we'll complete the equation. So tau v is given by what? VQ divided by IT, because this is an internal shear stress that's associated with a bending moment, even though the bending moment's small. And for V, we have got what? V is FA divided by 2 here. So FA divided by 2, and we didn't write down the value for what FA actually was. So here we go. We've got AY and AX right here. So remember that those were acting on our pin joint. So we had AX like this and AY like that. It's not a good place to put it. So the vector sum of these was our force FA. And of course we had it pointing in the opposite direction because we were drawing it on the pin. But FA will equal what? AX squared plus AY squared. You don't need this many sets of brackets here. AX squared plus AY squared to the 1/2 square root of that. Okay, so let's put in what our value for that is, and we can put that in our equation when we do it because that will be important. So we've got what? 10.5 squared plus 10.4 squared to the value of 1/2. And that gives us what? 14.8 kilonewtons. 14.8 kilonewtons when you do the math on that. Okay, so FA, there's our value of FA. So coming back over here, our internal shear force is FA divided by 2. So we've got 14.8 times 10 to the 3 divided by 2 for our value of V. And then Q, we want A prime, Y bar prime. So we're calculating the shear stress at point E, which the shear stress at point E is the shear stress shared by all points along the centroidal axis, or the axis that passes through point E and is perpendicular to our shear force. So for our area A prime for Q, we choose the portion of the cross section above or below that line that we're calculating the shear stress along. So that area right there. So that area is going to be what? Pi over 4d squared for area of a circle. So we've got pi over 8 and d squared there, recognizing that the d is not that d down there. Let's just change that to L so we're not confused. This d is the diameter of the pin. Okay, and then the centroid, or the centroidal location of A prime, we want that location relative to the centroid of the whole cross section, and that gives us our distance y bar prime. That's just the centroidal location of a semicircle, which is 4 times diameter over 6 pi. And then we divide by IT, so pi over 64 d to the 4th for the moment of inertia, and then t, the length of the line that we're calculating shear stress along, so that's the diameter as well. Okay, some things we can get rid of there. those guys, and we've got 3 Ds here, so we can get rid of that. There we go. Okay, so now we've actually got an expression for tau v, so we can return to this equation and complete it and solve for the required diameter of the pin. So let's do that. So sigma y we said was 207 megapascals for 304 stainless divided by our safety factor of 1.5 is equal to √3 multiplied by tau v. And here we've got our expression for tau v up here. We've got what, 14.8 times 10 to the 3 divided by 2 multiplied by what, 4 over 48 divided by pi d squared over 64. Pi d squared over 64. Okay, so pop this into your calculator, and when I did, what did I get for a value there? I got 12.6 millimeters. 12.6 millimeters. If we were rounding to the nearest millimeter, again, we'd have to go up to 13 millimeters for the required diameter of that pin. Okay, questions about that portion of the problem there? Give you a second to digest there while I get a drink of water. Okay. The putting on the axes and the orientation of this element wasn't so smooth on my part, so hopefully you didn't get confused there. Okay, let's go on and see what the next part of the problem asks, because we're almost done, but we're not quite done. One more part left. This question's actually not that long. If it was only one part, right? But because this is meant to demonstrate like a variety of things to you in terms of how the different failure theories relate to one another. So because it's got so many different parts in it to do that, then yeah, this one's a bit long. But if you were just without having to do all these parts, if it was just sort of size the cable, find the diameter of pin A, then it would be, you know, much shorter. Yeah. But for some of these questions that involve the application of the failure theories, and it's a 3-dimensional problem where you have an internal moment, an internal torque, maybe an internal shear force as well, you know, it can be a pretty long problem to work your way through the whole thing. But you won't have a couple of the problems on the problem set for this week, or the questions on the problem set for this week might be a bit longer, but certainly on the exam, in the format that the exam is in this year, you won't have any problems that are anything close to resembling this. Okay, so the final part of the problem, part 4, here says, what is the required diameter of pin A right, which we just found, if the absolute maximum shear stress theory was used instead. Okay, so we use the distortion energy theory here. It's asking what would the diameter have come out to be if we had used the absolute maximum shear stress theory. So the diameter of pin A if the absolute maximum shear stress theory were used. Okay. So we've done all the hard work for this one, right? This one's really easy now that we've done all the other work. So the absolute maximum shear stress theory, tau abs max, is equal to what? Sigma y divided by 2 times the safety factor. Absolute maximum shear stress, just look at Moore's circle. Because these principal stresses have different signs, one's negative, one's positive, this tells us that the absolute maximum shear stress is equal to the maximum shear stress, right, on this circle, which is equal to R, which is equal to our value tau V in this case, tau V. So going back here, we can just write tau V equals what? Sigma y divided by 2 times our safety factor. Okay. So looking at the difference between these equations, right? Here we've got sigma y divided by the safety factor. And if we move this over to the other side, 1 over root 3, sigma y divided by the safety factor, 1 over 2 instead of 1 over root 3 equals tau v equals tau v. So even though both of these failure theories, right, maximum distortion energy, absolute maximum shear stress theory, those were the same when we had a state of uniaxial normal stress. When we've got a state of shear stress, like we do now, then these theories are actually a little bit different. Okay, so they're going to give you slightly different answers. Okay, so let's see what the value comes out if we were to use this theory here. So we take tau v, which reduced to this equation here. Let's give ourselves a little bit more space. 14.8 times 10 to the 3 divided by 2, 4 over 48 divided by pi over 64 d squared is equal to our yield strength, 207 times 10 to the 6 pascals divided by 2 times our safety factor of 1.5. So diameter ends up being, when you crunch the numbers, what does the diameter end up being there? Let's see, 13.5 millimeters. Okay. 13.5 versus 12.6, right? So you end up with a slightly larger diameter if you're using the absolute maximum shear stress theory. And the absolute maximum shear stress theory, the great thing about it is that it's simple to apply. Like mathematically, it's very easy. You can see how the distortion energy theory can get very complex if each of these stresses, so the 2 principal stresses, sigma 1 and sigma 2, let's say had a couple of unknowns in them, then you end up with quite a complex equation here. But the absolute maximum shear stress theory predicts that failure will occur slightly before it actually will. So it underestimates the strength of materials by a little bit, and that leads to over design. So if you actually applied a load and you wanted to limit your stress to 207 divided by 1.5, then a pin of 12.6 diameters would actually do that. A pin of 13.5 diameters would actually have a safety factor that's slightly higher than 1.5. So absolute maximum shear stress theory, easy to apply, but leads to slight over design of components. Okay, so that brings us to the end of that multi-part problem. Any questions about that one there? Okay, not hearing any, so we'll do some erasing and then move on to the second problem. Yeah, I've been playing around with different things that we can do. So I'll try something new there. And look, we can bring up the second problem right on the screen there so that you guys can be reading about it while I'm erasing. All right, let's go ahead and look at this second problem that's up there. All right, so 1-inch diameter A36 steel bolt has rusted into place, right? You can see it right down there. It's rusted into where it's connected and needs to be removed. A socket wrench with a force F applied parallel to the x-axis. So it's nice, we've already got a coordinate system shown for us up here, is used to try and remove the bolt. Determine the maximum force F that can be applied before the bolt yields. Okay, all right. So this is one of these cases where we're given, a problem, but obviously we want to apply failure theory to it, but we're not given a particular point that we should be looking at. So we need to decide where in the bolt, which point will experience the maximum stress, which point should we apply our failure theory to. So the thing to do here is to take a section cut through the bolt and just look at what the internal forces are like, and then work from there. So put that down, and what we're going to do is we'll just draw sort of a simplified version of the loading situation that we have here. So here's the socket wrench, and we'll just draw this as a single sort of piece going right into the bolt, right? And then this comes sort of like, that's not a great, there we go. All right, where that's the connections there. So there's the nice picture over here. Here's my simplified picture over here. And that force is what? It's being applied like this, F. Okay, and then let's take those dimensions and actually put them over here. So this goes to the center like this. So what's that first dimension? I can't read it all the way up on my monitor over there. I've got my monitor dimmed way down so I don't see the reflection of the monitor in the glass and then back in the video. 10 inches. Here, 10 inches. And this distance here to the base is 6 inches. Okay. So if we want to explore the internal forces within the bolt, right? Let's just do a section cut through it somewhere. So relative to the actual bolt, right? We're doing like a section cut just somewhere through that bolt there. All right, so let's erase the rest of this here, and we'll make this look like a bit more of a proper. Wow, that's not a good attempt at all. There we go. It's better. Okay, so we want to stick our axes on here, and we said that we had axes in the problem that were already defined for us. So we've got X, Y, and Z like that. Okay, so X, Y, Z. There we go. All right, and this is no longer that length we showed. This is length L now, right, to the location of our section cut. Okay, so what do we need for internal forces, right? We've got a three-dimensional problem, so we need, if this is actually static, which it is, then some of the forces in the X needs to be 0, some of the forces in the Y needs to be 0, some of the forces in the Z needs to be 0, some of the moments about X, some of the moments about Y, some of the moments about Z, and then you look at the three moment equations and decide which one of those should be some of the torques. The Z-axis is the longitudinal axis of the bolt, so this should be sum of the torques about the Z-axis equals 0. Okay, some of the forces in the X direction, we've only got one applied force here, so, and that's in the X direction, so this needs to be equal to F. It's a force that's parallel to our section cut, so it's an internal shear force. Internal shear force along the X direction equals our applied load F. So we've got that one taken care of. No applied forces in the Y, no applied forces in the Z, don't need to worry about those. Some of the moments about the X-axis. Is our applied load creating a moment about the X-axis? No, it's not, because it's parallel to it. So it's got no component that's perpendicular to the X-axis. Some of the moments about the Y-axis. We've got load F perpendicular to the Y-axis. They don't cross one another in three-dimensional space. Load F is going to cause the torque wrench and the upper portion of this bolt to want to come over the Y-axis in this direction, so we need an internal moment in the opposite direction here, My. The value of My is going to be what? The force multiplied by the moment arm, so that's length L. So we've got My equals F times L there. Okay, I'll just move that Y down a little bit lower so it's not jammed up there. Okay, good, we've done that one. The torque about the Z-axis. Let's continue this Z-axis down a little bit. Yes. Force is perpendicular to the Z-axis. Two don't meet in three-dimensional space, so the force is going to cause the whole object to want to rotate about the Z-axis this way, so we need an opposite torque, TZ, like this. What's its value going to be? It's going to be the force multiplied by 10. So 10F. There we go. Okay, so we've got the internal forces shown that are in the bolt now, right? And it doesn't matter where in the bolt you take that section cut, right, you'd end up with the same internal forces. So we've got an internal torque, right? That would be the same along the whole length of the bolt. The internal shear force, again, doesn't matter where you cut in the bolt. And the internal moment here, the whole length of the bolt would have an internal moment in it. But because the moment is F multiplied by length L, we can see that the internal moment is going to get bigger as we move this section downwards. So the largest internal moment is going to be right down at the base here. Okay. So that's the location that we should be looking at for picking the point of maximum stress. We know that bending stresses due to internal moments are generally large compared to shear stresses caused by internal shear forces, with the exception of pins, which have very small moment and larger shear. Here, the moment is going to give rise to a normal stress that's significantly larger than the shear stress due to the internal shear force. Shear stresses due to torques, though, are generally significant. So what we want to do is look at the base of the bolt, and when we get to the base, we want to look for the point that experiences the maximum normal stress due to the bending moment and the maximum shear stress due to the torque, and see if we've got a point that will experience both of those together, maximum from both of those. All right, so let's just move this section cut all the way down to the base of the bolt here, and we can do that just by changing this L to a distance of 6 inches. 6 inches here, which means that instead of F times L now, this is 6F. There we go. So now we're down at the base. All right, what point do we want to choose here? Okay, if we look at this cross section, or look at this section cut in the ZX plane, so looking down the y-axis, right? Something like this, where we've got the x-axis going out this way, and we've got the z-axis going up that way, then we can see that our internal moment, and maybe I'll draw that internal moment a little bit lower there, our internal moment my is occurring around in this direction. So the normal stress resulting from this internal moment, it's going to be taking this side of the cross section, compressing it in on itself, taking this side, pulling it out in tension, and then we have a nice transition between the two, linear transition from tensile stress to compressive stress. So the maximum, because this cross section is round, it's symmetric, maximum tensile stress is going to be equal to maximum compressive stress. Maximum normal stress is going to be one of those points, either one, right? So looking at those 2 points up here on our cross section, one of those points is there, the compressive stress, and the tensile stress, maximum tensile stress, is over there. All right, what about the shear stress from the torque? Well, we know that shear stress from an internal torque, if we look down the z-axis, so we've got the x-axis going this way and the y-axis going that way, and our internal torques around that way. This is TZ. Then we know that internal shear stress due to an internal torque just increases as we move outwards from the center. So we've got a distribution of shear stress that looks like that if we're doing a radial line along the x-axis. Okay. So all points along the circumference will experience maximum shear stress from the torque. Okay. So we've got 2 points here. both those points experience maximum normal stress from the bending moment. Both those points would also experience maximum shear stress from the internal torque. So we want to choose one of those 2 points, and it doesn't matter which one we choose since the stress states will be equal. It's just one will have tensile stress on it and the other one will have compressive stress. So let's, it doesn't matter which one we choose. Let's just choose this one here. Okay, so let's call this our point B there. So choose point B, and we'll draw the volumetric element of the bit of material that's located at point B here and place the stresses on it. There we go. Now let's get rid of the that. So the section plane that, or the face of the element that's in the section plane is the bottom face here, right? And the rest of the element projects up into the remainder of the bolt. So we're going to put all of our stresses on that bottom face. Let's transfer our coordinate system, Z, Y, and X in that direction. Okay, so at point B, from the internal torque, we'll have a shear stress at point B. It will be, here's point B up here, right? It's going to be pointing in the direction of tau Z and tangent to the circumference at this location. So that's in the negative Y direction, right? So we come to our volumetric element and put a shear stress on in the negative Y direction like this, okay? And one up here, one there, and another one there. So this guy here is tau due to TZ. All right, our internal bending moment, we already said that there'll be, this is our location B here. We said that there'll be compressive normal stress there. So let's go and put on a compressive normal stress sigma due to My right there. For our internal shear force, because we've also got an internal shear force present, remember that if we draw a picture of our cross-section with the y-axis going out like this and the x-axis going out like this, and our internal shear force Vx is in that direction, then here at point B, where we're considering there is no shear stress due to Vx, because if we were to draw a line through point B that is perpendicular to the direction of the shear force, the area of the cross-section below that line, A prime, is 0. So this is our stress state for our element. So let's go ahead and calculate the values of sigma My and tau Tz. So sigma My is given by My over I. And our internal moment was 6F. Okay. Our distance Y is the distance that the point we're considering is away from the axis of the moment. So that is half the diameter. And the diameter of this in the problem statement was, what, 1 inch? Okay, so this diameter here is 1 inch. So distance Y here for My over I is ½ inch, 1/2, and then I pi over 64 d to the 4th power. What did I get when I did that calculation? 61.1 F in PSI. All right, shear stress, tau Tz is given by T rho divided by J. Our internal torque is 10F. Rho is the distance that our point of interest is away from the axis of the torque, so that's the radius, half an inch. And we've got J pi over 2, radius to the 4th power. All right, that gave me 50.9 F psi when I did that calculation. All right, so now we're at a position where we can sketch the in-plane representation of this volumetric element and then go and construct Moore's circle and apply the failure theory and solve for what load F is. So the in-plane representation of our volumetric element, here we go. We want to look at the volumetric element in the plane that will capture all of those stresses. So that would be in the ZY plane. So we've got Y, Z. There's sigma my. And tau Tz is going to be on the bottom, facing in that direction. You're pointing in that direction. And there we go. So this is tau Tz. Perfect. Okay, so let's set up our axes for Moore's circle and construct that. And then we'll be in a position to identify our principal stresses and, apply the failure theory. So Moore's circle. Here is our axis for shear stress and axis for normal stress there. All right, what do we need? We need the average normal stress, sigma average. In this case is 1/2 of what? Sigma z plus sigma y. Sigma y, which is equal to what? 1/2 of sigma z is 61.1 F, but it's negative because it's compressive, so minus 61.1 F. And then the normal stress in the y direction is 0. Okay. Perfect. So we've got minus 30.5, minus 30.5 F there. All right, so that gives us the location of the center of the circle. So minus 30.5 F. Again, don't be bothered by the fact that we've got an unknown there, right? We can still construct Moore's circle. The other point that we need, of course, is point A, which is the stress state of the element's right-hand side. Right, so here's the right-hand side. It's got no normal stress on it. So we're at 0, tau, and we've got tau Tz, it's upwards, so it's positive. Value is 50.9 F. 50.9 F. Okay. 0 and positive, that's downwards, so there we go. 50.9 F. And there's point A. So radius goes from C to A, like this. Here is radius R of the circle, and then we can draw the rest of the circle. Right, something like that. Not the most beautiful circle, but that's okay. The principal stresses which we're interested in, sigma 1 over there, since that's the larger value, sigma 2 over there, smaller of the magnitudes. Okay, so for either sigma 1 or sigma 2, sigma 1 is going to be the center of the circle minus the radius. Sigma 2, center of the circle plus the radius. So let's get the radius. What r is equal to the square root of that distance squared plus that distance squared. So we've got minus 30.5 f squared plus 50.9 f squared to 1/2. That gives us 59.4 f. Okay. So that means that sigma 1 is c minus r here, minus 30.5 f minus 59.4 f is what? Minus 89.9 f. Is that right? Yeah, looks right. 89.9 f. Sigma 2, c plus r, is minus 30.5 f plus 59.4 f equals, what have we got here? 28.9 positive. Okay. All right. Now that we have those values, now we can apply the failure theory. So here we go. We've got maximum distortion energy theory. Sigma y divided by our safety factor squared is sigma 1 squared minus the product of the principal stresses plus the second principal stress squared. All right, the bolt is an A36 bolt in US units. Always easy to remember the yield strength of an A36 steel object because the yield strength of A36 steel is 36 KSI. 36 times 10 to the 3 divided by our safety factor. We wanted to know what the maximum force that we could apply was before the bolt actually yields. So the safety factor is 1 in this case. Sigma 1, we've got minus 89.9 f. Square that minus the value of sigma 1 minus 89.9 f multiplied by sigma 2, 28.9 f plus the second principal stress, 28.9. Let's not forget our f in there, f, and square that. Okay, solve that for f. And we get 335 pounds. Maximum you'd be able to apply before yielding that bolt. And being the maximum distortion energy theory, the maximum distortion energy theory predicts failure very, very accurately. So this is actually the maximum load you'd be able to apply before that bolt yields. If you used the maximum absolute shear stress theory instead of the distortion energy theory, then you would get a value of force that is smaller than 335 because the maximum absolute shear stress theory slightly underestimates the strength of materials. Okay. All right. Questions about that problem? Questions about failure theory stuff in general, or anything else that we did? Those are the only two problems that we're going to do today. Okay, great. You should be fairly well set up to do the problem sets now. So go ahead and give them a try, and don't hesitate to contact me if you run into difficulties or get stuck, or just want to go through any other concepts. Okay. It doesn't matter, email or Microsoft Teams. They're both okay. Yeah, doesn't matter. If it's something that's like an easily answerable question over email, then that's fine. But if it's something that probably easier to do a bit more of an explanation for, then sometimes Teams can be better for that. Okay. Well, have a great day. Okay. See ya.